First. Yeah, hello everyone. Welcome to today's ASAP seminar. Today we are very happy to invite Tianyuan Zhang, an exceptional speaker from MIT CSL to talk about test time training done right. Tianyuan is a PhD student at MIT, advised by Professor Bill Freeman. Before that, he got his master in robotics at CMU, supervised by Professor Srivatsa Narasimhan. He has had research experience in machine learning, physics-based vision, computation, images, and computer graphics. His current focus is on video generation, word models, and infinite context learning. Let's welcome Tianyuan for today's talk.
Thanks. Also thanks Tianyuan and Songlin for hosting the seminar. Let me start. So today I will mostly talk about this project. And it's a project in joint collaboration between MIT and Adobe Research. And inside this team, I think maybe 90%, let me see, 80% of the team members work on computer vision tasks, including 3D computer vision and video generations. And probably 1 or 2 of the team members work on sequence models and the language models. So I think this paper has a very interesting background for community in this seminar talk. In this talk, I will definitely talk about some backgrounds of test training and why test training, why people want to do test training. And then I will talk about what does the title mean, why we name it test training done right. And then I think I want to spend maybe 60% or 70% of the time talk about details and insights about this work. And I think audience from this seminar are very high quality, and a lot of audience are very familiar with details on language model, details on new sequence model. So I want to spend more time talk about a lot of detailed experiments. So let me start by using one slide to talk about the major idea of this work and why we call it test time training done right. So the done right parts is basically told by this figure. This figure measures how much flops different operation can use, basically the hardware friendly or hardware throughput of different operations. And if you test or if you use the open source code from the original test time training paper, the TTT-MLP and the TTT linear, it achieves around 3 to 5%, below 3 to 5% of the flops utilizations. And what we do is we just do a very simple change, and you can achieve 50% to 70% of the GPU utilizations. And here, the blue dotted line on the top, on the A100 and H100, are the peaks flops for these two hardware. And how we achieve that? It's just a very simple modification. We just use a very large online bar size when you do test training. That seems very trivial, but it will have a lot of interesting implications, which we will talk about in the talk. And since the bar size term is used in a lot of different places, we only change the test training bar size, online bar size. We call it chunk size, so that don't cause further confusion when people talk about bar size. So we name it the methods as locked large chunk size test training. Now I want to spend a few slides talk about what is test training and why people want to do test training. And I think the words test training definitely have different meaning for different researchers. And I will cover the most general meaning of it. What's the most general definition? What's the general picture when people talk about test training? And also I will talk about a more narrow understanding of test training. So what does the general meaning mean? For general meaning, we want to start from most currently training paradigm. Current training paradigm mostly starts from pre-training, where you want to compress the word knowledge, not a lot of knowledges into your neural network. Then it follows by a stage of post-training. You can do reinforcement post-training, or you can do supervised fine-tuning, or you can just want to fine-tune for other tasks. And by post-training, you can understand that by you want to draw a small circle in the big map. This small circle maybe entails a subset of data, or this small circle enforce a subset of behaviors you want a model to pick up. So the general meaning is that you want a model to be more specialized in something, either in problem following or either in reasoning or either in some small task. That's what maybe some way to describe the meaning of post-training. And here comes the testament training, in that after pre-training and maybe after post-training, when you deploy the model in some test time environment, and you want the models continue to learn or continue to adapt in that environment. And you might hope during testing training, the model may be even more specialized, or maybe more customized or personalized, or the model can just understand the test time environment better to just do something better. And I think that's the most general meaning of testing training. It's just seems to be a new stage, the final stage of learning of some models. So this is proposed by Sun Yu, who has been doing testing training maybe starting from 2018 or 2019. And he has a website maintaining a lot of his work on testing training. And I would refer readers with interest to read that webpage. So here we cover the general meaning of testing training, but in this talk, I wouldn't go very deep in this talk. So I want to check the chat box. I think some people might, okay, feel free to drop any questions here. But in this talk, I wouldn't go very deep into the general meaning, into the new stage of training. If you are very interested in that, you can also read this work. I think the first work comes from colleagues at MIT last year, December or November. And in this talk, I will mostly talk about a more narrow understanding of test training. Is people use test training as an idea or as a new framework to design new sequence models. Okay, and I will cover what does it mean and some examples of it. So first, very background. What does a sequence models mean? Here, I think the word I use sequence. When I use sequence, the word is a little bit overused. It does not necessarily mean 1D order sequence. It just means a lot of tokens. So sequence models mean you get a lot of tokens as input and you get a lot of tokens as output. And these tokens can be 1D order text, can be images, videos, audios, a lot of different data. And one dimension of the input token, the sequence length dimension, it means how many tokens you're processing. And currently, major or most powerful and popular sequence models are transformers. And inside transformer, just the two type operation. One is MLP, and one is attention, which is the most bottleneck operation of transformer attention. And attention has some interesting properties. First of all, a lot of basics. When the query token came in, what attention does is just look up every previous token in the KV cache and then do some linear weighted sum as output. And the attention has a lot of interesting properties. Here, I listed 3 properties. First of all, the cost for new tokens is growing. The cost for new tokens is linearly growing. The memory footprint and the computational cost is linearly growing. This for some people think it's a bug. The second property that it does not do any in-context compression. It does not compress past tokens. It just keep a copy of past KV cache. And the third property is that it has very high parallelism, degree of parallelism on the sequence length dimension. So the second property and the third property, some people think it's a bug, some people think it's a feature. I don't know. I think people have different understandings. But these properties inspires or incentivize a lot of people to design new sequence models. Either new sequence model will have cheaper cost, or new sequence model do some in-context compression, or new sequence model have different level of parallelism at a sequence dimensions. And recurrent neural networks or recurrent memory modules or memory modules are the most dominant new sequence models. And here, I also want to start from some basic slides. I want to use a notation of attention to introduce some basic understanding of a memory module or recurrent memories. A lot of different RNN papers use different notations. I want to unify in the attention notations to make understanding more easy. So suppose you have a KV cache. Maybe you want a language model to read a book, and the KV cache, this is a KV cache book. What you do is that each token will be split into a key and the values. That's the notation of attention. You have a key and the values, and it's paired. You have a key and the corresponding values. And what you do is you want to compress the key and the values into a memory module. Here, you don't need to think about what is a memory module. We will talk about that later. You just want to compress the key values, pair the key value associations into this memory module. And when new token came in, when you want to answer some questions in the future, when some future token came in, this query token would not attend directly with key and values. It will attend with the memory modules, right, and get the output. And if you look at this framework, it has two basic operations. One is memory update. You want to update your memory module to store past informations. Another operation is called memory queries, right? When a new token came in, you not only update the memory, you also want to query the memory to get some output. And I think test training gives a simple way or principled way to define new memory update and new memory query operations. And here I want to introduce using some notations. Suppose you want to process a sequence of tokens. The sequence suppose n tokens. Each token x1, x2, xi is a d-dimensional vector. Okay. It can be causal. Suppose it's causal in time. And following the notation of attention, you want to split each query into each token x into query key value. It's paired. And the test training first introduce a new notation. You want to adapt part of a model's weight at test time. These weights are typically called fast weight. It's typically part of a neural network, part of your whole neural network. And it can be one layer of your neural network, or it can be a separate MLP inside your neural network. We typically call it a fast weight function. You can call it a fast weight function. It's conceptually related. I don't think the original test training paper call it, but I want to call it as a fast weight. Okay. And this fast weight function can be a linear layer or MLP layer, just a parametric function. The parameter is W. It's a d-dimensional input output to another d-dimensional vector. And the W, the weights of the fast weight, is online adapted in the current sequence. We're going to adapt these weights for this input sequence X. And the adapted weights will store the memory of the input sequence. And this fast weight can be anything. It just be a parametric function. It can be a linear network or MLP, or even a transformer if you want to do that. Okay. And then now with this basic notation, here comes the test training. It defines the memory update as online gradient descent under certain objectives. It's because you want to adapt to the fast weight W through some way of a gradient descent. And the gradient descent is trying to minimize this loss function L. Okay. Here I use a specific notation. The loss L is a function between value and fk. You can use some other notation, but the majority of the work use this notation. It's a loss defined on the k and v's. Okay. So update as online gradient descent. And here the loss function is you want to design anything you want. And the common loss function is key value associations. This L, for example, could be the dot product, the negative dot product between fk and v, or L2 loss between fk and v. So all of these loss are called key value association loss or key value reconstruction loss. Its meaning is just you want to enforce the model, the fast weight function, to memorize the mapping between k to v, basically to memorize the associations between k and values. That's the underlying meaning of this loss function. Oh, here is it. I want to answer some questions in the chat. So the question is fast weights conceptually the same as LoRa, as primary efficient fine tuning? I think it's two different concepts. Parameter efficient fine tuning is a parameterization of the parameter. Phosphate is just a part of your neural network. It's a part of the model you want to adapt at test time. You can think of phosphate as a recurrent state of a RNN. Okay, let me continue. Here, I want to use a very simple diagram to detail this process. For example, you have 4 K tokens and 4 value tokens. It's paired K value tokens. And you want to update your memory module to memorize these K values. What do is you first pass the K tokens to your phosphate. Suppose you want to use the MLP layer as a phosphate function. You pass it through the function, and it will predict some tokens, right? And we call it the output token, the predict token, as retrieved values. And what you want to do next is you want to compute the pairwise loss between the retrieved values and the true values. And then you do one-step gradient descent to update your memory module. So that's a memory update. That's what test and training do. You test time at a test time, you adapt this phosphate function to memorize key value associations. And you can by doing gradient descent. Okay, this is a memory update operation. And another operation we talked about previously is you have the updated memory. What do you want to do for new tokens, right? The memory query, you want to retrieve the memory, you want to query the memory. What do is you just pass the query token to the phosphate function to get the output. And that's it, very simple. It's straightforward pass of the memory model. So here's a small summary of the output operation. Oh, sorry, a small illustration of the output operation, the memory query operation. You just use a query token and pass it to the updated memory module to get the output token. And here's a small summary. The update can be done through some gradient descent between the loss function defined on the K and the values, on the retrieved value and the values. And then the apply operation is just a forward pass of the updated memory module. Right. Okay, so after talking about how test and training can be used to design the update, to design the memory module in principal way, I want to emphasize one point, is that this test and training, it opens a vast design space. It opens this framework has a very, very big design space. I think that's one of the major contributions of the TET paper. For example, the design space can be in the phosphate function. You can use a linear layer or a nonlinear layer or any neural network, any parameterized function as a phosphate function. Second, the online training objectives, right? You can use dot product loss, you can use L2 loss. Or you don't want to use key value association loss. You can use the next home prediction loss. You can use next frame prediction loss. Or you can maybe use the different models, denoising loss, or anything you want. As long as it's self-supervised, you can use it at test time. Another interesting design space is the online optimizers, right? You can use vanilla gradient descent, or you can use more sophisticated ones. For example, gradient descent with momentums. And in this talk, I also use Moon as a new optimizer and also organize the updates. Okay, some details. Some people say, hey, does test and training, if you do test and training this way, does it compute second order gradients? I would say from my definition, it's just a chain rule. It's just a longer chain rule. For example, in the forward pass of the test and training layer, you have these two operations. You have a weight update operation, and then you have the memory query operation. And when you get the output, you get the final real loss. You do the backpropagation to compute gradients to update your whole model. The gradients will fly through the output to W and Q, and then flow from W and Q to the initial phosphate W and the K and V. So it's just a longer backproper chain. And this backproper chain just have a lot of matrix multiplication. So I don't think, I don't call it a second order gradients. Maybe it is. There is no something like Jacobian vector product or something. and all of them are Matmos. And I don't think it will have, maybe it will have some numerical problem. I don't know. I don't think it will have. I just feel it's just make the model deeper in some sense. Okay. So that's some background details about TASM training on using TASM training to design new sequence models. And here I want to talk about one important aspect when you want to do this. So you want to make the TASM training layer hardware friendly. You want to use the hardware as much as possible. And there are some certain aspects I want to emphasize when you do that. The first thing is about tensor cores. So this is a screenshot of specs about an H100 GPU, last generation GPU. It has a number called bfloat16 tensor core as around 2000 teraflops. Normally for dense matrices, it's around 1000 tera floating operation per second. So what does it mean? It means that theoretically, this GPU can do around 1000 trillion floating point operation per second for dense Matmos. I want to emphasize this point. It's for dense Matmos. If you do matrix vector multiplication, it cannot reach this number. What does Matmos mean? It means it at least you want to multiply a two-dimensional matrices with another two-dimensional matrices, and the minimal size of the matrices is 16. So that being said, if you want to do a matrix vector multiplication, you probably need to pad the vector 16 times, which means you can only achieve a GPU utilization below 8% if you only have to do matrices vector multiplications. So basically, tensor core says you want to make every operation inside your model try to be matrices multiplication as much as possible. You don't want to do matrix vector multiplications. And that implies when you want to do TASM trainings, if you want to do TASM training for each token, each token, if you only want to do for that for one token, basically you want to compute gradients for one key and value pair, this operation will contain a lot of matrix vector multiplications. No matter how the fast wave function look like, no matter how the loss looks like, it's just a matrix vector multiplications, right? So to able to use the 2D Matmos, to able to use the tensor core quite well, you need at least online mean size larger or equal than 16. So then when you compute the loss, you just sum over 16 vectors. When you sum over 16 vectors, you just do a matrix multiplication, where the minimal size matrix 16. And this has already been done. This strategy has already been adapted by existing TASM training methods. Oh, one message in the chat. Yeah, I think this is, so the question is, we should have second order gradients with respect to the initial fast wave. I think it's true, but you don't materialize that. It's just computed through chain rules. And for sure, the initial fast wave is optimized. Okay. And this online mini burst is already adapted by current existing methods. But I want to comment out existing majority of them use a mini burst size of 16 or 64. The second aspect, okay, I think there's another message in the chat. Okay. The second aspect for hardware friendly is about compute intensity. What does it mean? It means that if you look at the specs, we talk about how much floating point operation can be done within each second. Another important metric is memory bandwidth. So H100 has around 3.35 terabytes number of read and writes per second. And an important metric is you want to divide the compute with the memory. So which means H100, on H100, the time of reading one byte, the same time, you can do around 300 flops at that time. So this gives you an implication in that when you read one byte in your layer, inside your model, when you read one byte, you want to do a lot of flops. You want to do at least hundreds of flops so that you can use the hardware enough. Right? So this defines an operation, a metric, which is the number compute divided by the number of memory read and write. And if you look at that metric for test sum training, that metric is always smaller than the test sum training bear size. You can derive this number, suppose using a simple linear function as a test training layer. I don't think using different layer will change the conclusion very much. It's just bounded by the test training bear size. So this gives you implication that you want to use the test training bear size as large as possible. I think at least around 200 or 500 to be able to make the operation as a compute bound rather than memory bound. Right. Okay, and another aspect is your operation, your whole layer, your model should be able to be parallelized on a lot of degrees, should be able to parallelize on a lot of dimensions, because for modern GPUs, one GPU have around 100 compute cores. And if you want to parallelize in multiple GPUs, it have thousands of compute cores, right? And this cores execute parallel. So you want your model to be able to parallelize in so many degree of freedom, so many degrees. And if you look at the whole model, there are typically 3 dimensions that you can do parallel. One is batch dimension, which is trivial. All model can do that. Mostly all model can do that. The second dimension is feature dimension channel, a feature dimension. We also call it heads dimension because following notation of attention, you split the QPV through different heads, and the compute among heads are totally parallelizable. So that dimension is also trivially parallelized. Another important dimension is sequence length dimension. Imagine a use case where you want to train the model or inference the model, mostly train the model on very, very, very long sequences. Under that case, typically your batch size per device, per GPU is 1. Your heads dimension may be around 16 or 4 or 8 or 20 or something. In that case, if your model is not able to parallelize on the sequence length dimension, you will definitely not be able to use a full compute cores within one GPU. So be able to parallelize on the sequence length dimension is very important. And most linear attention and flash and quadratic softmax attention can be parallelized in the sequence length dimension. Right. But for the test sum training with the nonlinear weights, well, nonlinear fast weights, if we want to parallelize on the sequence length dimension, the only thing you can do is to parallelize land within the bear size, because across test sum training bear size, it is a sequential. It's non-linearly sequential, and the only thing can parallel on the sequence length dimension is your online bear size. I think another question in the chat. Yeah, arithmetic intensity. Thank you. Thank you. So after this 3 slides analysis, I think all of this leads to a common solution is use an extremely large test sum training bear size. Here we call the test sum training bear size the chunk size. So what does it mean? So suppose you have a lot of tokens as the input. What we do is you want to sort of split these tokens into different chunks, and each chunk can contain thousands. In this paper, we use the maximal chunk size is 1 million token. So you want to first split lots of tokens into chunks, large chunks. And for each chunk, you update the fast weight once. Right? You use a bear size of maybe a few thousand tokens to update the fast weight once. And we call it large chunk test sum training. And this is trivially can use 2D MetaModes and have high arithmetic intensity and have high degree of parallelism. Not as high as attention, but higher than nonlinear TTTs, previous nonlinear TTTs. Yes, and another interesting point in that if you use a high GPU, a high TTT bear size, you only need to write PyTorch code. You don't need to write kernel codes. And I think this is in general very good for the research community because this can make your research iterations much faster. One thing I want to comment, if you do this large chunk size updates and you design a sequence model following this principle, the question is, what's the data topology you're operating on? Right. I think this operation is designed for sequence of set. let me explain a little bit. So when you update the phosphate using a chunk of tokens, this update operations that ignores the orders within the chunk, right? Ignores the order and the localities of tokens within the chunk, right? It just treats the token as a set of tokens. It has no orders. It has no topology information embedded, right? And we update each chunk sequentially. You update once, update another chunk, update another chunk, and update another chunk. This is done sequentially, and this is done causally. So it's a causal between chunks and orderless within chunks. So it's natively designed for sequence of set. And you can use position encodings within the set or window attentions within the set to help you model topologies within the set or help you do something else, which I will talk about later. The second property then, I empirically found if you use a large chunk size, the locality is not handled quite well. I think, I think for handle locality for this phosphate, I think it's non-trivial. It's just no better than attention. So what do we do throughout this work now? We always use sliding window attention or window attention with this large chunk layer. And this window attention will handle localities in the data. And by doing that, you can use a TTT. TT has limited state size. You can use the state size better to handle long memories. So one intuition I want to comment is actually Songling quoted another one's words. It's called the enemy of the memory is other memories. Suppose you don't have this window attention to handle localities. What you need to do is you will constantly swap in local memories to your TTT states. Right? You will constantly swap in memory and swap out and swap new local memory and swap out new local memories. So if you don't have window attention, your TTT you need to constantly swap in, swap out, swap in, swap out, which intuitively is not good for long memories. That's only intuitions. And this strategy of using sliding window attention or quadratic window attention to handle locality and a recurrent model to handle long memories is also adopting a lot of other works. Okay, so we have covered most of the design points on this paper. Next, I want to cover some details. In this paper, for the testament training layer, we use a sweet glue MLP as a phosphate. We use it because a lot of language models use it. Just people use it everywhere. So we use the same sweet glue MLP as a phosphate. And the sweet glue MLP can be spelled in this way. It has three weights, three matrices, W1, W2, and W3. And it has a nonlinear activation of silu. And it's a silu gates on another linear output. And we want to adapt this W1, W3, W2 at the test time to minimize this key value association loss. We use a negative dot product as key value association loss. Okay. And so we have the phosphate function, we have the loss, and we use different type of optimizer. We have used a vanilla gradient descent, we have used the MOA, we have used the momentum, but all of them after the gradients updates, we will do a weight NOR. We will do a weight NOR. For example, you have the current phosphate W, you have the update G, you do one gradient descent. After that, we do L2 NOR channel-wise. So this W is, for example, D by D, we do at the last dimension. It's like a channel width. It's very similar to the post NOR, So for example, let me see this. For example, very conceptually, you update your phosphate horizontally through time. You rotate this 90 degree and treat it as a virtual model, treat it as a depth of virtual model. So you treat the time of the recurrent model as a depth of another virtual model. This L2 norm is conceptually the post norm some people use in transformers. Okay, now I want to cover some experiments. So we did 3 different data structures, also 3 different tasks. And the first task is novel view synthesis. It takes a set of images as input. Different image has no orders. The second experiment is language model. It takes one order sequences. And we also do autoregressive video diffusion. I think this talk, I will mostly talk about experiments in language models and also some experiments for the novel view synthesis. So let me start from the language model experiments. There's one question in the chat. Let me check. So the question is, any reason why such a shallow MLP works so well? This MLP has two layers. The sweet glue MLP have two layers. We tried a linear layer. Sweet glue is better than linear layer. We also tried 4-layer deep MLP with residual connections. It works. I didn't validate a lot. I think it's on par or better than the 2-layer MLP, sweet glue MLP. But what do we do is we just don't want to introduce too much design space into it. We just use a common use sweet glue MLP. Maybe there are some benefits of a deeper memory, but I don't know. I think there might be, but I don't know. And also for this model, if you want to increase the capacity, you can make it wider in the hidden dimension, right? The hidden dimension can be 2 times, 4 times, 8 times wider than the input X dimension. And this makes your implementation easier. So for the language model experiments, one thing I want to comment on, there is a definition of a chunk size, online test training batch size in the design, in the model. And for languages, there seems not to be some common chunk structure in languages. I think there are, but I think there might be, but we didn't. Maybe in the future you can use the concept episodes as a chunk size, but for now we just use a hyperparameter of 2,000 tokens or 8,000 tokens as chunk size. It's just a hyperparameter. The second thing is language model need per token causality. Okay, and if you do large chunk test training, you have you have conceptually attention mass of a blockwise causal. You don't have per token causal attention mass. You have blockwise causal mass, right? Because within each chunk, it's bidirectional. Across chunk is causal. So what we do is we use sliding window attention to the causal to do the per token causality. So some details. When a new token came in here, before the detail, I want to talk about the order between the update and the apply. Apply is a memory query, which we talk about. In the paper, we call it apply. And update is a memory update. The orders between update and apply actually entail different attention mask. If you update the fast way first and you apply, it has attention mask of this, right? Block-like causal. And if you apply first, if you use the initial fast way to apply to current queries, current batch queries, then update fast way, it has a shifted blockwise causal mask. The blockwise comma is shifted by one chunk, and this prevents you leak informations. And in language model experiments, we use this apply first, then update operations. So you use the initial fast way. So for the first chunk of token, in your language sequences, it does not have anything. The fast way does not have any information about the first chunk, and then you directly apply the fast way to the first chunk. Then you update. And the per token causality is done by the sliding window attention. So for the TDT mask, it has a shifted blockwise causal. And for the sliding window attention, it has a per token causality. And when you combine these two, it has an overall per token causality causal mask. Okay. And some details is that we mix the sliding window attention into the same layer as a locked layer, as a TDT layer. The QKV is shared. And the way we share the QKV follows this paper of gated attention units. For example, you split the QKV, you get the QKV, you multiply the key QK with a learnable scale and the shifts. Basically, you use a learnable scale and the shifts to apply to the Q and the K, and use them for the softmax attention. And the original QKV is used for the TT layer, and you add the results. So more detail can be seen in the paper. Now I want to cover some baseline. So the first baseline is a transformer baseline, and also transformer with sliding window attentions. We also measure the training throughput token per second on 4 A100, 4 GPU of A100. All of the code is using the Flame framework. It's open source language model training, and it supports the flash linear attention. So for the linear attention baseline, we compare with gated linear attention and the delta net, and all of them has the same sliding window attention as ours. The state size is measured per block. So the delta net has head dimension of 128. So the state size is 128 times the model dimension. Okay. And for ours, we call it large chunk recurrences. We have different three variants: the gradient descent, vanilla gradient descent one, the gradient descent with momentum, and the gradient descent with moon. Moon has momentum within it, and the state size is 10 times larger. So we use 4 heads. This is measured for a 3 billion parameter model with a hidden dimension of 3,000. So the state size is around 2,000. And this is a training token per second. Okay, and some details. So we train it with 32,000 sequence lengths. So we use a very high rope base of 1 million. And this rope base is used whenever attention is used. For example, it's used in the full attention, it's used in the sliding window attention, it's used in the hybrid sliding window attention. It's used whenever softmax attention is used. And for the gated linear attention, we remove the output gates. Okay, and the value will have a full dimension. The default one, the value has half the dimension. So the QKV has a full dimension. For the delta net, we remove the short count because all ours have no short count, no output gates. We just remove this extra stuff. And the one thing I want to comment on, our design have the initial fast weight. We try to make the parameter the same, but we haven't made that. So we have around 3%, smaller than 3% extra weights. The majority of the extra weights is the initial fast weight. The initial fast weight is initialized through a low rank parameterization to save parameters. We put that in the page 25 of the paper. One question in the chat. Yeah, the question is, do you avoid double counting attention between overlapping tokens within TTT chunk and the sliding window attention regions? So the sliding window attention is a default per token sliding window attention. And the TTT, so I don't think if not answer question. The sliding window attention is just a per token.
Yeah, I think his question is like, do you separate? So for different token, each token is only handled by sliding window attention or the TTT update. I think in our model we both for layer 5 token, they are handled by both sliding window attention and the TTT, right?
There is overlap. There is overlap. Yeah, there is overlap. We don't do anything to avoid the overlap. There is overlap. Okay. Experiment setup. We do experiment at 2 scales. The data sets is a Together's data set. It has around 16.8 billion tokens. We train 2 parameter scales. One is 700 million parameter. One is 3 billion parameters. All of them use sequence length 32,000 tokens, and we have different chunk size. So for the smaller one, we use chunk size 2,000. For the larger one, we use chunk size 4,000. Okay. For evaluation, we do 2 things. One is we want to measure validation loss on different token positions. Here, validation loss is computed in the box 3 data sets. Also measure the retrieval accuracy. Here, I want to start from the first results, the validation loss on different token positions. We compare transformer, all of this. Here is a small scale experiment. There are a lot of curves. Let's start from the attention curve, the full attention curve, the blue one. The x-axis means different token positions, right? We have training sequence length of 32,000, so we only measure up to that sequence length. The y-axis is the maximum prediction loss at that token position. So this figure, we make the similar style as a forgetting transformer paper. We use their style. It's not the perplexity up to the sequence length. It's a loss at this token position. I think this is like the gradients of the perplexity, because perplexity is a weighted average. If you look at the blue line, it's very beautiful. I think it's very beautiful. It's nearly a line on these log scale plots. Okay, and the green line is the sliding window tension. Okay, and the yellow line is gated linear tension with sliding window tension. And if you look at the green and the purple one, the purple one is ours with momentum. The green one is dirt net. The red one is ours with more, which is much slower and better. Okay, this is a 700 million parameter scale experiment. Let me show the 3 billion parameter experiment. One thing, if you compare the blue with the gray, if you compare full attention with sliding window tension, one interesting happens. For the small scale, the sliding window tension is better than full attention up to around 4,000 token lengths. But for the 3 billion scale, it's just the same. I think because the small model, there's a trade-off between further tokens and closer tokens. But for the larger model, there's no such trade-off. Second, we have the second is that our momentum in our moon has better performance compared to gated linear tension, much better than much better than the small scale, because here we have even larger state size. The third thing I want to comment out is the green line, the dirt net one. It seems the results a little bit off. I don't know why. I didn't tune any hyperparameter. We use the same hyperparameter as a small scale and large scale, and there are more gradient specs on the dirt net one. I do think another tuning, using different hyperparameter for the dirt net one, we have better results. Let me answer one question in the chat. Yeah, forgetting transformer.
Sorry, can I ask a quick question?
Yeah, go ahead.
So as you mentioned, like for the two figures, like the green one, delta net, I mean, in the first figure, it's much better than GLA, but in the second figure, it's much worse than GLA. So do you think like it's some hyperparameters or it's
I think it's hyperparameter. I think it's a hyperparameter. All of this parameter is one shot. We use learning rate of 1e minus 3 and initialize it with 0.02.
So in the first figure, like that net, it's even like slightly better than the momentum one, right? So do you think like if we highly like tune the hyperparameters in the 3 billion skill sets, then it can achieve like similar performance of the momentum or even more? Or or you think like it should be slightly worse? Or
I don't know. I think there's a lot of space.
okay, thank you.
Yeah, I would like to add that. So here is like I think it's probably due to like hyperparameter searching or stuff like that. But I think the most important here to deliver is that whether this model can like the loss curve will keep decreasing when increasing the amount of context that the model can use. So like for gating linear tension, due to the decaying factor, the model seems not to use that much historical context. And we all know that gated irons are mostly very similar to some soft version of sliding window tension. But for delta net, it does not have the explicit decay return. And it seems that when increasing the context size, the delta net can better leverage the more context. And I think this one is more important because in terms of the loss curve, it has better slope when increasing the number of historical token.
Yeah. I want to add more details to this. So Sonny mentioned one detail some people may not realize. For the gated linear tension, the gate in the title, gated linear tension, means you want to decay your state exponentially. The state is the past tokens decayed exponentially. And for the delta net, it has no such term. Gated delta net has that term. For ours, we don't have such exponential decay term. We have a weight NOR, which also do some decay, right? You always make the previous one smaller, but the decay is much slower. And if you look at the yellow curve, the gated linear tension one, all of them have much flat slope for maybe sequence length up to 8,000. And I think now maybe because maybe it comes from the exponential decay one. And I think that's one insight people gain. If you want a model to really handle long memory, you want to avoid such explicit exponential decay.
Sorry, another quick question. So can you briefly describe your validation data?
The validation data comes from book 3. We evaluate on 2.5 billion tokens for the small scale and 5 billion tokens for the 3 billion parameter experiments.
Okay, thank you.
Here is a retrieval accuracy, single needle in a haystack. It has 3 different difficulty. We show the first 2 difficulty. We didn't show others. Others are in the paper. If you look at other ones, the accuracy is a little bit trivial. So we highlight a single needle hashtag 1 and a single needle hashtag 2. I actually don't understand why the transformer has lower accuracy here. Maybe because of randomness. But if you look at 3 billion one, attention basically just to do perfect on this task. And all the compression ones has worse task. But here, Albert's moon has much better accuracy. Another experiment is state size scaling. So we try to keep everything fixed. The number of parameters change through experiment slightly. We use different state size, right? And here we measure the validation loss of the last 2,000 tokens, So this is done at the small scale, the 700 million parameter scale. We increase the state size by reducing the number of heads. So when you use the smaller and smaller number of heads, your state size will increase linearly. And one thing I want to comment out, this is 3 Glulam LP with moon updates. Okay, I will revisit some new language experiments later. For now, I want to show this novel view synthesis experiment. I think a lot of audience in this talk are not familiar with this task, but I want to show it. So the input, this task is about if I give you 100 images of this room. I give you 100 images of this room, or 100 images of your apartment, 100 images of the classroom, or something. And then I will, in the future, I will ask you, if I place a camera here, what will the photo looks like, right? So the input is a lot of images of the static scene, and also a query camera pose of some novel camera viewpoints. And you want the model to output the RGB pixels of the viewpoints, right? So here is, for example, the bottom 16 images are input images. The rendered videos are model's outputs. Okay, so why this task? This task is a smart retrieval task. It's very different from Pascal retrieval. I will explain. So why is the retrieval is simple? Because all the information about novel views are given, right? All the information about novel view are given. Your model does not need to store this room looks like this square looks like this outdoor scene looks like this. Your model does not need to store anything. All the information is given to you at the test time. I call it smart retrieval because you need to do some 3D reasoning. It's not copy paste. You need to do some small 3D reasoning. Second, it's a compression rather than global random access. So Pascal retrieval is global random access because all of the context is irrelevant and you hide something in that. Here it's compression because if I give you 200 images, I think 80% of the information is redundant. Right? If we give you 200 images of the room, 80% of the information is redundant. You can compress a lot. You don't need to memory every pixel of the image. You just need to compress into a compact 3D representation. So it's a smart retrieval task. I think it makes more sense to test. If you want to test on global random access, like Pascal retrieval, I don't think that's what linear attention is designed for, right? That task requires global random access. You need to use attention or RAG to do that. So this is more like smart retrieval. I think it's a better test case. Second, it supports testing at a different sequence length because you can use different resolution, different number of input images. So and also it has some golden matrices as a rendered novel view. The quality of rendered novel view. And here I want to show also this experiments, we do a very interesting experiment. We use an extremely large chunk set, extremely large. The maximal chunk size 1 million tokens. So I want to show some detailed architecture. For example, we have 3 posed input images of the room, 3 input images with camera pose. Camera pose means each pixel, you have some coordinates indicating the direction of each pixel. So it's some physical correct positional encoding. So this task does not require any positional encoding. Okay, that's also a very important property. You do an image per image local and attention to handle locality per image local. Then you have a lot of input tokens, up to 1 million input tokens. Then you update your memory once through one gradient descent. Okay, just update once. Then in the future, there are some novel view came in, some target camera viewpoints came in. This novel view is just the coordinates which pixel as a query position coding. And then you query the memory module one, or you do some pre-image attention. Then you query the memory module once to get the output of the novel views. Right. So it looks like this. It just you use green tokens, input image tokens, to update the memory ones. And for the novel camera viewpoints, you just directly do query. And this update operation is like prefill, right? We give you 1 million token, you do prefill. And the query is like decode. Right. There's a question in the chat. Yes, the camera array position coding is plug array. What is the base model for this task? I will mention that. So conceptually, there are two stages. One is prefill, right? You have a lot of input image with this camera pose, which is a plug array. If you don't understand what's a plug array, that's fine. Just some physically correct positional encodings. Okay. You do pre-image attention, then you use all of the token to update the memory once. Very large chunk size. And then you do query to render novel views. It's a prefill and then it's a decode. And the decode cost is constant, no matter how much input image you have, right? Because you do compression. So memory update is conceptual like prefill, and the memory readout is like decode. The decoding is fixed cost. I put some number here if you're familiar with 3D. So when you do decode to render new images, the whole model will become a static VIT, right? After the prefill, the whole model will become a static per image VIT, variant transformer. And it has 30 IPS on A100s for such image resolutions. So we do 3 baseline. The base model is a full attention. So this attention, it also have a prefill and decode. It has a blockwise causal mask. What does it mean? So we replace a locked layer with 2 attentions. The first attention is all the input image attention, all the input image token attend with each other. It's a full bidirectional attention between input image tokens. It's a quadratic cost attention. And when you render novel view, the novel view tokens cross-attend with input tokens. So it's like a blockwise causal mask. The first block is a prefill. The second block is the cross-attention when you do decode. Okay. So this baseline does not do any compression, right? It keeps the KV cache of all input tokens. We also get so here we summarize some characteristic. The state size grow linearly to your input token. The prefill compute is quadratic. The decoding compute is linear. Right? Another baseline, we do attention with compression. It's just a register attention or perceiver style attention. So we replace a locked layer with 2 attentions. First is input to register full attention. You have a lot of input tokens, 1 million input tokens, and you have 4,000 register tokens. You do a full attention between register and input. You compress the input information to your register. You want to use softmax attention with register as a compression, as a prefill. When novel view token came in, you attend with a register token. You don't attend with input. Input is gone. Okay, so this attention with compression. Here we summarize some statistics. So the state size for the full attention is growing, but for the perceiver attention and for the TDT it's 0.1. The prefill compute, all of them, all the attention one has a quadratic cost. The decoding has some linear and some constant. So here's the prefill compute speed and rendering speed. I want to also comment all this pre-image attention is applied for all the baselines. Okay, the speed is tested on A100s with 200,000 image input tokens. And we do experiments on 2 different data sets. One is image object data sets, which is easy, right? The object has limited information. A lot of them are compression, maybe 90% information is redundant. The second data set is a scene data set. The object data set is object-verse. Scene data set is a DL3DV. Sorry, I didn't put the reference here. I should put the reference here. It's called DL3DV. Okay. Non-data sets, we use up to 128 images as input, which is exactly 1 million tokens. But non-data set has up to 300 images and up to 4K resolution, which is 100 million input tokens. We didn't do that scale. We just do this scale. Okay. I want to first show the object results on object data sets. Comparison between full attention and register attention. The x-axis shows different number of input tokens. The y-axis shows different number of the PSNR. And our model is trained for, I think, around 600 billion tokens, 600 billion tokens on the object data sets. So two conclusions. One, we are just behind full attention, but not too much. That's interesting. I think for a task, if you need global random access, the gap is much larger. But for a task that there are a lot of redundant information and you want to compress that redundant information, the gap is smaller. Okay. Second, the attention with register or attention with compression is much worse. So the state size is similar. The green one has 4,000 tokens, and the red one have state size of 4,600 times smaller dimension. So the state size is similar, but the attention with compression is just much worse. Here I have an intuition. I will explain the intuitions very, very briefly. If you don't understand that, if you didn't get it, that's fine. Because just intuition, I don't know if it's correct or wrong. When you have a memory module, when you want to do compression and then later do retrieval, there's a trade-off between retrieval sparsity or retrieval accuracy and the amount of information you can remember. If you want a very, very sparse, very, very crispy retrieval, you need to store your memory quite orthogonally. Then you don't have too much space to store information. So you cannot store that much. So I think there's a trade-off between retrieval accuracy and the amount of information you can retrieve. And attention is very sparse, so it can do sparse retrieval, but it cannot memorize much. That's my intuition. I don't know if it's correct or wrong. Here I replot this figure at a higher resolution. The x-axis is just a time, prefill time. The y-axis is PSNR. The peak PSNR of TDT is worse, but the cost effectiveness is much better. Here's one question in the chat. If we do same in pre-training, how? So we fix the training tokens. We fix the amount of training tokens. I think if your training sequence length exists, is longer than 16K in this setup, locked is efficient than full attention. And if your sequence length is 100K, locked is much efficient, trained much faster than the full attention. Because one is linear cost, one is quadratic cost. I think the threshold is around 16,000 tokens, something between 10K and 20K thousand tokens, where the speed is the same.
Sorry, basically what I mean, I'm trying to understand, maybe I'm completely off, that, you know, basically it's a kind of test time training, it's a kind of zero shot, multiple shot, you know, answers, right? So the base model should be able to do the same thing, right? Basically. So now you have a trade-off. Either you do it during pre-training to adjust your base model parameters, so you could do it after fine-tuning. And so you could compare efficiency, or maybe your methods would work also during in the pre-training or fine-tuning phase. Or I just completely miss the target.
I don't fully get the question.
Say what, suppose your task is you show several views and request your query would be the image from a different point of view, right?
Yes.
Okay, so what's the base model to, because you do test time training on top of some kind of pre-existing model. So what would the base model do? It's supposed to doing the same thing, maybe in a different domain, right?
Let me answer. I think I get your question. So we don't do test training on top of base model. Test time training inspires the design space of a new sequence model. So test training is not test time training. It's a new sequence model. It's a new recurrent model. It's just a recurrent model. And you want to compare this recurrent model with the tensions, with transformers.
Okay, so you're saying when you do test time training, you don't start with any base model parameter, but you say 3 billion parameter model, right?
Yeah. So
Mhm.
test time training, it's an idea. It's a framework. Inside the framework, you can design a sequence mixer, a sequence model, a recurrent model. And that recurrent model is just like RNN. It's just trained from scratch on your whole data sets. It's just like a transformer, but its compute cost is linear.
Okay, so you don't need to have any pre-existing data or any base model.
You don't.
You just start from, okay, thank you.
Yeah, it's just a new RNN, and you train an
Okay.
RNN from scratch, and also you train the baseline transformer from scratch, and you compare the two sequence models.
Okay, understood. Okay,
And
great.
here, and the previous slides, just show the experimental comparison with them.
Okay.
Okay. And here we show some results on the same data set. If you do language model, you can forgot about these slides. This comparison is compare the green dot. The green line is called 3D Gaussian spotting. It's an optimization base. It's some traditional inverse graphics methods on this task. It's basically one of the state of arts on this task. It is give you 100 images. This green line will do 10 minutes of optimization and come up some explicit 3D representation of the scene. And we outperform them up to 100 images. But for 300 images, we are worse than them. And also the 3D Gaussian spotting one can do much faster, can render much faster. It's just here just showing comparison with neurally learned 3D representation and handcrafted graphics people crafted 3D representation, such comparison. It's very, very interesting to see such comparison. And the green line is a previously SOTA data-driven methods. Here are some video results. I don't want to show that because it's just hard to understand. And also this one, I will skip them, and I want to show some very interesting new results, very interesting ablations. So one is state size scaling. It's just trivial. Larger state, better results. Here we also for all of this task, we show results on novel synthesis and the language models. Right here, I shows state size is different from 0.3 to 12 dimension square, different state size. You can see just the results are better and better as you increase state size. But I want to comment, the flops is increasing quite a lot. The parameter is also increasing. Second, I think this is very interesting. So I want to compare different test time training optimizers. Okay, the yellow line is gradient descent. The green line is more. For the novel view synthesize, we just do one gradient update, so there's no momentum. But for the language model, we do multiple updates, so there's a momentum. It's autoregressively updated. And so here there are three terms: vanilla gradient descent with momentum, momentum plus Moon. Moon does orthogonalization on the final momentum outputs. That's very interesting. And also gradients will flow through the Moon's iterations, through the orthogonal iterations, right? When people typically use Moon, when you use in pretrain, you don't need Moon to be differentiable. Here we need Moon to be differentiable, and that's quite interesting. Another thing I want to comment is Moon has two properties. One, it is expensive. It's expensive to orthogonize matrices. So if your chunk size is small, say a few hundreds, the cost for doing Moon, doing the orthogonalization, is larger than the cost to do the forward pass of that layer. So you need a large chunk size, around 2,000, 4,000 is enough. Second, Moon does orthogonalization on the updates, right? Which means if you have a low rank matrices, suppose your matrix dimension is 100 and your rank is 10. When you do Moon, it does not give you a 10 rank matrices. It still give you 100 rank matrices. The rest 90 ranks are noise because of numerical problems. So Moon will magnify some noise ranks. So if you use a small online minibar size, I would afraid that Moon, I'm not sure. My intuition that Moon will not be very good. You need the update to be effectively high rank so that Moon can perform better. And to do that, you either need a large byte size or you do the momentum, right? Momentum just to do sliding window average of the updates, which basically increase the effective rank size. But some question, do you compare reducing chunk size while increasing state size in AutoCAPE? No. So the question is, do you compare reducing chunk size while increasing state size in order to keep arithmetic intensity high? I think this is wrong. You need your when do you have the best arithmetic intensity? When your head dimension is the same as your chunk size. Right? When your head dimension is the same as chunk size. And here I think head dimension is either 384 or 768. And the chunk size 2000. For language model experiments. I didn't do that.
Sorry, I guess I was trying to ask, yeah, you emphasized how important keeping arithmetic intensity high is in order to create efficiency.
Mhm.
Oh, I see Songlin was answering a bit. Yeah, I guess I was just wondering if you could get away with a slightly smaller chunk size, like you were saying, maybe 512, but still have it be, maybe a head size of something like 512 in order to create high arithmetic intensity and still have a lot of flops per memory access.
Yeah, I think your intuition is correct. And it's only in common on that you need more degree of parallelism so that you can have a high occupancy on your GPUs. If you use byte size 1, and if you have 4 heads, H100 have 100 streaming multiprocessors, you cannot use all of them. You need to have large sequence dimension, large head dimension to cut them into multiple cores.
Gotcha. Thank you.
Yeah, but if you have a high byte size, so when you test the flops of some operations, if you use a small byte size, you will see the flops are low. But if you increase the byte size by 2x, you will see the flops also increase by 2x, which means you haven't used a full tensor cores for streaming multiprocessors. Also, I think one interesting that in the novel view synthesis experiments, we have 1 million chunk size, and we do sequence parallel within chunk. So we cut the chunk, 1 million token in the chunk into 8 GPUs. And if you don't have a high chunk size, you cannot do that. Another very core experiment I want to comment on is you mentioned the advantage of GPU efficiency, etc. What's the disadvantage when you use chunk, right? People will realize you are treating sequential steps for parallelism, right? You have fewer sequential steps, you have a higher parallelism. That seems the trade-off we are making. And what's the disadvantage of such trade-off, right? So I call it a chunk recurrences versus per token recurrence. Okay. The answer is mixed. For the novel view synthesized experiments, right? Where the data structure has chunk, we compare the blue line. The blue line is ours linear, so we would do a linear memory, and the light blue one is Mamba. We keep the state size the same, and for Mamba, because it's causal, so we have 2 layers of Mamba inside each layer. One is from right to left, one is from left to right, and we add the 2 results together. So the state size is matched, and the Mamba has higher flops, but the Mamba is per token recurrence, and ours is per chunk recurrence, and ours is better. Maybe because some details is not aligned, but here the result is ours better. And for the language models, here I want you to compare the blue one with the yellow one. The yellow one is gated linear attention with sliding window attention. The blue one is ours linear with the same state size as the yellow one. The only difference now, so here is a linear chunk recurrence. Here is a gated linear per token recurrence. We don't have the gates. Right? So you can see that when you have the same state size, on languages, we are worse than gate JLA. The chunk recurrence is worse. Right? But if you, yeah, I want to highlight this. But if you add more state and more nonlinear, we get the red one. That's the story. Because for the chunk recurrence, I think it's designed for nonlinear memories. Because a linear memory has associative properties, you can do particular recursive quite fast. You don't need a chunk recurrence. Chunk recurrence is only for nonlinear memory. It's only for parallelizing nonlinear memories. Okay, I think that's an interesting experiment. I do think that the chunk recurrence on languages can still be further improved to mitigate the gap between the blue one and the yellow one. And also, I do think that languages have chunk structure, such as episodes, such as when you read the abstract of the paper, that's one chunk. When you read the introduction, when you read this paragraph, that's one chunk. Or when we finish the discussion of one topic, that's one chunk. But here, we just ignore such structure. We just use a hyperparameter chunk size. The second thing is linear memory versus nonlinear memory. Here is a blue one on this experiment of linear memory. And all the linear memory will like to have larger state size than the nonlinear one. For example, here the linear memory is 1.5 times larger than nonlinear memory, but it's just worse. Okay, so I think that's most of the experiments. And for the summary, I think you just memorize that large chunk size. That's it, large chunk size, boosts the GPU utilization and makes research iteration faster. And also the idea that use TTT for long memory and window tension for local memory. Yeah. So I can stop here and take any questions. Thank you.
Yeah, maybe I can ask a question that based on your previous observations that do you think that if we still use token-wise recurrence but increase the state size, it will be much stronger than the nonlinear ones? Because that it seems that currently that when you both have small size, that the linear ones with token level recurrence is better. So that why we needed to choose a nonlinear one with large chunk size instead of just scaling up the state size of the token level recurrence?
Yeah, that's a good question. So I think scaling state size always helps, no matter from linear and nonlinear. Second, I think nonlinear, in my experience, just always better than linear at the same step, at the same flops, at the same parameter, at the same flops. So sometimes I think you do want to go nonlinear. It just give you better flop trade-off. As for the token recurrence versus chunk recurrence, I think for some data structure, chunk recurrence is good. But for languages, I'm not sure, but I do think nonlinear with large chunk seems have higher upper limits. That's my understanding. It opens more scaling. That's my understanding.
I see.
Yeah, I think there are some fundamental theoretical limitations here also regarding the linear memory. Yeah, you know, like in Titans, in TTTs, they highlight the importance of nonlinear multi-layer perception, this sort of neural memory, right? And I think that like so you can imagine like the fast weight as like a feed-forward network is just weight matrix used to store those information. In FF, from the perspective of FFN, if you only have a single linear projection, you'd like to have a very wide a single linear projection to have a large memory capacity, but with two layers of this nonlinear memory, you don't need to have a very, very wide model dimension. And this is why we prefer to have deeper network instead of like one single very wide neural network. And I think this is very similar to the case of fast-weight programming, right? And in fast-weight, those nonlinear recurrent memory is theoretically more like has more capacity to store those information using smaller state size, because after all, you cannot scale the state size indefinitely, right? So this is where you want to use some more better strategy to leverage this fixed size memory, and this is my current understanding. And I believe like nonlinear recurrent memory is like the future for non-sequence modeling. Although I've done a lot of like linear memory in this area, but I do believe like nonlinear recurrent memory is the future, and we should work more on this area. And this is why I found like this TT downright paper is like very interesting exploration in this area.
Also, one thing I want to comment. So I do think nonlinear have better scaling behavior, as mentioned by Sony. Also, nonlinear give you larger design space. In general, I think that's helpful. And I do believe some points in that design space is significant, maybe not significantly better, just better.
Hi.
Hi.
I would like to carry on with this line of discussion. I just have a question. Do you think if we stack more layers in the online MLP, would that increase effectively as if you were increasing the number of transformer layers in the slow weight models?
Oh, sorry, can you repeat?
So basically, I was asked. So basically, I interpret the current model is basically have a single layer of MLP serve as the fast weight in your online MLP, right?
Yes.
And you stack multiple layers of such fast weight as the home model. So basically, I was asking, do you think it will make sense that if you stack multiple layers in a single fast weight MLP?
Yeah. So your question is, for the fast weight layer, does going deeper in that layer give you better something?
Yeah,
yes.
I think his question is like, so instead of stacking multiple transform layer, you can span those parameters within your single layer fast weight, right? And then
exactly.
During
the more precise
fast-weight recurrent update, you can have a multiple layer like this kind of fast-weight programmer instead of like sticking to the same amount of total layer. So you can view this fast-weight programming layer as multiple transformer layer, and then you can use those multiple layers parameter as part of the fast-weight, right? Yeah, I think this is his question.
Yeah, I agree with Sony on this interpretation.
I do have one more comment. So if you look at history, when people start from AlexNet, VGGNet, and just 10 layer something, and the ResNet goes to 100 layers, and the layer people show that deep neural goes to 1000 layers, some similar work. Okay, when you stack more layer within your fast weight, you're increasing your real depth size, right? You have another depth size. That depth dimension is your number of updates. And I don't know if current mechanism can directly do that stably and performantly, right? I think maybe some new change, some tiny change of where the norm is, or something, how you better make the gradients more stable would make the nonlinear, very deep nonlinear fastway work.
I see.
I think I don't know if you directly do the current, you just make the sweet glue deeper, will not work. I don't know. Also, there are questions, do your fastway has residual connections? I don't. I think there are some detailed technical questions you want to make correct so that your nonlinear memory, deeper nonlinear memory will really be performant.
Sure, thank you. Basically, I think the higher level question I was having in mind was that if we keep the number of parameters constant, can we see there is trade-off curves between how many parameters you put in the fast weight versus putting in the slow weight? Do we have like certain curves showing you which method would be better? I understand that unfortunately for now we don't have that results. I would just like to open up a discussion on this, and the motivation for me to think about that was basically more from the system, perspective, because as long as you stack more layers, assuming the gradient stability problem got solved, if you stack more layers in your fast weight, it's gonna create a more asynchronous memory operation opportunities, in the sense that you can basically create a mega kernel for a single layer, and that would benefit a lot for the system perspective.
I think it makes sense. And also for the deeper nonlinear memory, you have more optimization space
Right.
in hardware.
Yeah.
Yeah, and I think apart from the system perspective, I think this question is like very interesting from the also from the machine learning perspective. Like if you only have a fixed amount of parameters, where do the parameters more worthy to spend on, like on this like multi-layer like a slow weight, or like in this like single layer fast weight? Yeah, and maybe you can have several layers of fast weight for each fast weight layer, and they reduce the total amount of layer by that percentage. And so to keep the entire number of parameters the same. Yeah, which is a very interesting question, and we unfortunately we didn't investigate it for now. Yeah, it's definitely a very interesting question.
Yeah, and for this, when you make the same flops, make the same parameter, and you compare, I think that's a very good way to do. We only did that for the momentum versus gradient descent. The flop similar, parameter is similar, momentum is better in language. Also the linear versus nonlinear. For the momentum versus moon has more flops, but the amount of flop is not that much, but the results better. So we want to equalize flops parameter. You definitely get more indicators, and the next part is actually non-trivial to do.
Right, I understand it's very non-trivial. And apart from that, I don't think flops matters that a lot, because with that system level of optimization opportunities, the flops metric might not be as indicative as the end-to-end latency would be, right?
Yeah.
So what I mean is that by stacking more layers, by spending more parameters onto the fast weight nonlinear MLPs online, maybe for a machine learning perspective, your parameters are better spent on more worthy positions. And second, you might be able to get more effective flops. So basically, you cannot compare the flops doing a fast weight versus doing the traditional flops. They are, the system has been quite complicated nowadays. It's not any more comparable.
Yeah, that's interesting.
Sure. Yeah, thank you for this discussion.
I wanted to ask about the potential for interference in, like, for example, in a multi-document context. So like, the fast weights might, be simultaneously storing potentially contradictory information.
I see.
And so, like, how would you mitigate that? Like, could you use, like, I don't know, a mixture of fast weights where you have different heads specializing in different memory slots with learnable routing or something? Or I don't know. How would you think about that?
Let me break this question. One is, if you have a super long document, you just have so many information, how can you store them? For that, I think increasing state size definitely helps. That's one thing. Second comment is, if you look at the online training objective, key value associations, if your KV cache, suppose you have 1 million token within your KV cache, if these tokens are IID, suppose just totally random, you will not be able to compress too much, right? If your KV cache is very related, as in the case of a novel view synthesis experiment, I think you can do a lot of compression. So I think this second point brings to your full question. If you have two pieces of documents totally independent, or even sometimes contradictory. Contradictory is another question. I don't know how to answer that. If you are totally independent, you definitely need a much more state size. And we do use multi-heads. Multi-heads is basically a subset of independence. And for the MOE you mentioned, mixture experts for the pathway, I think it will help, but it's non-trivial to make it efficient.
What about, like, maybe having some kind of a memory pressure signal that, like, could trigger selective forgetting when the fast weight capacity is saturated?
I see. I don't know. I think that's an idea to explore. And then this reminds me or make me thought of another idea is that can people do RAG, right? Retrieval augmented generation, where you have a database.
Mhm.
Can you have a database of fast memories? Right. That's just some random thinking. You have a database. Suppose you read this question, read this article, you got a fast weight. You store the fast weight to there. You read another article, you store there. And in the future, someone asks you, what's your thought about this article? You retrieve the memory back. I don't know. I just it's just let me think about a random question. But if selective is one thing, but when you do selective, you definitely need to forget something, right? The enemy and memory is memory, it's other memory. So increasing state size might be the only way, and that's my feeling.
Okay, cool. Thanks.
Yeah, I think apart from purely increasing the state size, maybe like a deeper neural memory is like also is very worthy to try. I think in Titans they show that they have a very interesting figure showing that like the higher the number of like nonlinear layer in that multi-layer perception neural memory, and the better performance. And they also control the state size, indicating that okay, this like deeper memory is also very interesting to try.
Yeah. I think in the chat there's a question from Rainer. What would you expect for task needing more nonlinear processing of pass input? Novel view synthesize seems to rely on near affine transformation. What if that's not enough? First comment, I think novel view synthesize, when you have a more complex thing, affine transformation is not enough. Near affine transformation is mostly for far away things, for planar things, far away planar things. What is the task that's more nonlinear process of pass tokens? I think if I were you, I might think another question is the key value association loss seems a little bit trivial, seems no reasoning behind. Will the loss makes a difference for some task or not? I think all of the question I cannot answer. I don't have too much intuition. What's the task needs more nonlinear? Also the question, what's the task needs more reasoning objectives? I don't know. What would I expect? And I think if it is a retrieval task, if it's a simple retrieval, maybe linear and nonlinear doesn't matter. If it's a global random access type of task, maybe linear and nonlinear doesn't matter. And if it's a more understanding level task, maybe nonlinear helps. That's my feeling.
Yeah, I think in my opinion, even for like this global access retrieval task, the nonlinear reality also helps a lot. And I think like for this sort of like associative memory, I think Anthropic previously have a blog post discussing the superposition phenomenon. And it's that like when you have nonlinear memory, for each neuron, you can have once the neural memory is nonlinear, you can have some sort of like superposition phenomenon. So each neuron can store more information, but for linear memory, there's no way to have such like superposition phenomenon. And this is why like linear recurrent memory is like totally bounded by the state size.
I think that's interesting.
Yeah.
Okay. May I try to like kind of ask again? Basically, there is a trade-off between slow weights and fast weights, right? Slow weights, you take some data, train a model, then freeze it, and then how you get
Persistent memory, right?
Yeah, then during test time, you take another data and then how you derive your first weight. So basically you have a trade-off. You could put the same data in training for slow weights or fast weights. So how would you compare efficiency which data put where, because it's just basically two different things to the same goal, right? To different ways to achieve the same.
I see. My understanding of your question is, now in the model there is a fast weight and there's a slow weight. How much should you use for each when you think about a trade-off?
And in this area, the methods for pre-training, the efficiency, how it compares to efficiency of your test time training methods. Is it the same efficiency per the unit of data?
It's the same. It's the same. It's the same. Just the way you do computation at pre-training and later fine-tuning is the same. And the way you do inference and pre-training is slightly different, but not too much different. So the efficiency is the same.
So do your methods are they applicable to pre-training as well?
Yes, yes. Majority of the experiments in this paper is trained from scratch. It's like pre-training. Because this is because test time training, a narrow understanding of test training is that it's just a new sequence models. It's just a new RNN. It's just a new model trained from scratch. During training, you also adapt your fast weights per batch. Right? If you think about attention, if you think about transformer, what attention does is you have a KV cache. You can interpret the KV cache as a weight of a MLP with softmax activation. Linear, softmax, linear. The first linear is K, the second linear is V of your KV cache. That you can also call that as fast weight, right? So in pre-training at each batch, you have a step update fast weight, and you have a step of query. The behavior is the same at inference. It's just a new RNN.
Okay, so the same efficiency. So I'm just thinking about memory mosaics approach, you know, because they have the same trade-off. I mean, you could either keep your data as is, or you could compress it into some parameters. For the to build the you know, the full transformer output. So you could do it both ways, and they just basically show that it's basically equivalent to a transformer wherever you just do smoothing between, or some kind of Gaussian kernel interpolation between sequences, and don't compress them into parameters, or you could compress them into parameters. It's the same kind of situation here, right?
Actually I didn't get this. Sony, do you get this, or can you help me answer this? Or Xinyu, do you? I think you understand the memory mosaic more.
Sorry, can you repeat the question?
Yeah, I mean, how would we relate it to memory mosaics, basically, where you have two ways to deal with data? You could either compress them, right, into parameters, or you could just keep them and do kind of interpolate during runtime, which is like test time, right? Similar to a test time inference. Or maybe I'm missing something.
So are you saying like in memory mosaic they have the like separation between different memory, like they have a long memory and short memory?
I think he made me talk about
they have parameters and they have data instances they keep. So some data is compressed in parameters, and some data
from my understanding, I think that parameter metric memory definitely it can maybe just during training that it have a better compressed ratio, but the problem is that parameter memory is hard to be trained that during inference time. Just means that you have some context. You cannot just always just do online just the gradient back forward and backward. It is very slow. Yeah, so that for the online memory, we will typically use a fast weight and update this fast weight. Yeah, I think from the capability that fast weight should be still worse than the slow weight or the parameter, but it's easy to be trained. Yeah, it can be efficiently updated at inference time. This is the reason why we call it test time training. Yeah. This is my understanding. I'm not sure whether Sony has some other understanding.
Yeah, no.
Okay, thank you. It's just trying to, because they're very similar setups, right? So it would be good to understand how they relate to each other.
I think, if you guys don't mind, I think I can shed some light on maybe what the idea is here. So I work on some models related to RWKV, and there we talk about something in between the two sides that you're talking about, which is state tuning. And that's used in this paper too, but although I think it uses a different name for it. And that's when you take the starting weights for the fast weights and you use a training process to find which ones would best fit the data that you're putting in. And that's actually a new type of in-between pre-training. It's like a post-train pre-training of the fast weights. So I think there are three varieties here. There's pre-training, there's whatever we want to call that in-between state tuning, and then there's test time. And the pre-training is, I think what maybe you're asking about is how expensive is pre-training to achieve the same result that you would get from test time? And the answer is it's much, much more expensive. And the reason it's more expensive is partly because you have to go through the full backpropagation process, which is typically like 3 times as many flops to begin with. And the model, you have to update all of the weights of the model, which is much, much bigger than these weights that are in the test time training weights. So it's like a much larger number of weights. But there is this in-between thing of state tuning where you can take a set of data and fine tune just the starting state for that. And so that's another kind of optimization process you can go through. And that's an in-between cost. It's typically much faster and cheaper than full pre-training or fine tuning, but it's more expensive than test time run. And so that might help inform the question a little bit better, maybe. I'm not sure.
Yes, okay, it helps. Thank you.
Yeah, thank you for this. And for the state tuning you mentioned, I think I understand your points. And in this paper, it's merged in the pre-training. The slow weights and also the initial states is trained together during pre-training.
Yeah, did you guys do any looking into seeing whether doing that state tuning was then beneficial to
It is.
continue doing it like separately for a specific data set?
This I don't do, but I have your question of, is learnable initial state helpful or not? It is. So if you have a random initialized initial state and fix it, does not tune it through all your stage, that's just give you worse results with a learnable initial states. And I think that's also be done by the original TTT paper.
Yeah, I know there are some other papers that have, and maybe Memory Mosaics had this, have varying state tuned starting states that they choose based on the input data. They somehow classify it and then decide to start from different starting points, essentially, which is another interesting in between that you can train multiple in a way that's a little bit like that idea you just were presenting about doing a almost RAG for this. I think there are some papers that do a little bit of something like that, where they sort of pre-train a bunch of these look-upable starting states and then choose one, depending on what kind of thing they're using.
I see. I read the Mary Mosa paper very, very briefly. I think I should check it out again.
Yeah, I also don't remember it very well, sorry.
I don't think there is anything about starting states. I mean, the whole premise is basically you're just purely keeping your data instances in memory. You could build a structure that would work absolutely the same way as transformer. So it's equivalent. You could either compress your data in parameters, or you could keep it as data instances in memory, or you have a combination of both. That's why mosaics.
Thank you. Thank you.
Yeah, and I think I have one more questions about the figure 5 in the original paper, that I find that when you train the 706 million versions that and test it compared with the transformer. Find
Mhm.
out when it comes to 16K and 32K that the transformers that have worse retrieval ability
Yeah.
in comparison with maybe both AlterNet and your method. I guess that do you think that this phenomenon is maybe because that we only have maybe fixed number of parameter and even we have so very long context length and very large memory for the transformer, maybe the model itself cannot handle such a large memory. So that I guess that
Ah.
do there exist maybe an optimal just as maybe something like scaling that between the model size and maybe the state size. Just means that if you only have this size of the model, even you increase the state size, it do not help. Yeah.
I see your question. Very interesting. So your question is for this figure B, the blue curve has actually lower retrieval
Yeah, yeah.
accuracy. And your interpretation that for this scale, for the transformer, the state size, which is the KV cache size here, is much larger. The portion of the state size compared to full parameter is just so large that the model cannot handle it. So if that is the case, if there is some optimal correlation between the portion of state size and the portion weight. Oh, that's very interesting question. I didn't think about that. I think that's interesting. And actually, I have one more evidence for that. Is one more evidence for your speculation in that. If you look at this scale, if you compare these two, full attention and sliding window attention, you'll realize that the sliding window attention is better here,
Yeah.
which I think is a little bit abnormal, I would say. But for the 3B scale, we'll compare the sliding window attention with full attention. It's just the same.
Yeah, yeah. And we can also find the 3B model that can do nearly perfect on the retrieval time.
Yes.
Yeah.
And I think it's like for this small scale, it just full attention need to spend a lot of efforts to handle this large KV cache so that it just degrades some performance somewhere. But for the 3B scale, the parameter is up, the state size is the same, and not the same, slightly larger, and the attention can handle that more better. So the full sequence length is just always better than sliding window attention. And yeah, it seems like to handle some state size, you need some amount of slow parameter. Otherwise, you always lost something, you lose something.
It just I'm thinking about if there is some kind of a linear correlation that maybe a fixed state size will be a correct item that may be a very large one. Also, yeah.
Yeah, I do think so. I
I
think
really like this conclusion, but I have an alternate hypothesis, which is
Mhm.
that maybe the hidden dimension is actually the thing that you need to increase the size of in order to address a larger KV cache size. And that is might not be the intelligence of the MLPs that is directly related, but it might actually just be the width. And so it's able to store more sort of like information about what lies where in a given, like in a compressed fashion in a given hidden state. It's just an idea, but it might be an alternative hypothesis.
yeah, I see your interpretation. Your interpretation is more focused on the attention layer. You need a higher head dimension for such size of KV cache.
Yeah, exactly.
Yeah, might be also
Yeah, this also makes sense because that attention also mixes many information into one single state. Also, they have many states, so that we just say that it is a very large memory state, but we cannot say that it is optimally just store the information or allocate them into different states. Just maybe some states is still just they still lose many information. Yeah.
And you also might have more heads in the larger model, and that
Yeah.
might allow it to address more different pieces of information separately.
Yeah, I think that will be very interesting to see some curve. If you have this amount of parameter or this amount of head dimension, what's the critical sequence length you can get for some behavior?
Yeah, I would love to see a whole paper just on that. It sounds so good.
Mhm.
So you mentioned reasoning several times. So what is this main connection you think between these nonlinear memories and reasoning? How do you see it? Because I haven't read the paper, but you said that nonlinear memories are helpful with reasoning or something like that.
I don't fully get the question. You're saying I was referring to some paper which
You
says-
referred no. You referred to something about reasoning and how having nonlinear memories.
Oh,
Nonlinear relationship between keys and values is helpful for reasoning. So what do you mean?
that's just a speculation. I don't know. So it's like when does nonlinear helps a lot? What task really requires nonlinear? Some we have an interpretation that nonlinear is helpful in a lot of cases, even in the simple case for retrieval, because nonlinear memory can have more polysemanticity, which can basically store something more. Superposition of memories, and Anthropic have a series of blog showing the concept of a monosemanticity and the polysemanticity stored in the slow weights of the MLPs. He was referring to that piece of article. I don't have too much insight on this, and I
Yeah,
also
but-
don't have too much insight on if nonlinear memory can help reasoning. I hope it's true.
Yeah, but what do you think? Like, if you think about reasoning, which I don't know if it is a good way to think about it, it is helpful. Reasoning as some kind of task finding problem in a latent space. And path is also some kind of a sequence. Is it like some, do you think there is some kind of, this approach could help? Basically, we are trying to find typically like reasoning path between point A and point B, if B we know the answer, right? And point A is where we are now. It's like some kind of verifies intuition.
My intuition is yes, nonlinear will help, but I cannot give you conclusion or something.
I think one potential reason is that if you consider the linear memory, one problem is that if you can consider one previously people explored the the parameter ones, maybe some linear layers. For example, even you have many linear layers, they can be just combined into as one linear layer, so that it do not actually maybe increase something like called the depth of the model. So maybe when some reasoning task get really maybe you can many multi-step reasoning that like state tracking, that this synthetic task they cannot maybe solved by a linear memory. But when you have the non-linear memory, the thing is that maybe this is maybe just orthogonal to the superposition hypothesis. This is just that it is actually that you cannot combine together, so you actually have the depth. So maybe you can solve a more deeper reasoning problem. This is, I think, that the previous that what they call that maybe the depth scaling, something like this. Yeah.
Yeah, basically one way to think of reasoning is just generate longer sequences, right? Like in this current paradigm. So, and when you generate longer sequences, I call it reasoning typically, right? But the question is, where would these longer sequences lead? Or it could be just wander aimlessly, or it would lead where you wanted to go into the right direction. So that's what I'm thinking about.
Yeah, I think this is still an open question that long sequence that how do scaling, yeah, how it helps reasoning, yeah.
Yes, it is, yes.
It's maybe approaching 2 hours. If there's no more questions, that I think that we can stop here. Yeah, thank you everyone for joining us today, and thanks Tianyuan for today's talk.
Thank you. Thank you for hosting and thank you for the great discussions.